All right, welcome back. So today I'm going to talk about separable equations and how to solve them. So here's the outline. I'm going to give you the definition of how to identify when you see something that is separable, and then I'm going to show you how to solve them in general, give you some examples, and then I'm going to conclude this lecture with a reminder. So the definition is if the right-hand side of the equation, this function that we have over here, can be expressed as two separate functions, g of x and p of y. We call that separable. In other words, we have dy over dx is equal to a function of x and a function of y. And that's what we mean by separable. We can separate out the function of x and a function of y. So before we figure out how to solve them, let's figure out how to recognize them first. Now this first example that I have is dy over dx is equal to a function of just y. And if you remember this is actually autonomous. Now what this says is that there really is no function of x on the right hand side, but I can write it this way. Dy over dx is equal to 1 times 4y squared minus 3y plus 1. And so my dy over dx is equal to g of x. But g of x is just this constant, and that's okay. A lot of students think it's not, but that's perfectly a legitimate g of x, just a constant function. And our p of y corresponds to that function that we have, that little polynomial in terms of y. And so this is, in fact, separable. In the second equation, we have dy over dx is equal to x squared plus y squared. And because of this addition here, there's nothing really I can do to take out a y or an x and just turn that into multiplication. If I bring the y squared to the left-hand side, that doesn't fix anything. If I divide everything through by y squared, again, that doesn't fix anything. So this is actually not separable. Now let's look over here at equation 3. Now this one is written slightly different than the other ones. The dy and the dx are separate, and that's okay. Step 1 is we want to put the dy over dx together to see if we can find anything. So the first thing I'm going to do is I'm going to divide each term through by 2x times dx. So what I get now is x times y squared plus 3y squared times dy. This is going to be divided by 2x, because remember I'm dividing every single term by 2x dx, and then I'll just put the dx right underneath the dy, minus 1 is equal to 0, because 0 divided by anything is also 0. Now I'm going to bring the 1 to the other side by adding 1 to both terms, or both sides I should say. So I have x y squared plus 3y squared divided by 2x dy over dx is equal to 1. And then to solve for the dy over dx by itself, I'm just going to multiply the term in front by its reciprocal. And so then I get dy over dx is equal to 2x divided by x y squared plus 3y squared. Now we're almost done. What I can do now is factor out a y squared out of the denominator. So if I do that, I have 1 over y squared. If I factor that out, and then I'm left with 2x divided by x plus 3. And so you see that this is going to be a function of just y by itself, and this is just a function of x by itself. So this is in fact separable. Now this next example, or the last example, number 4, I have dw over dt, so I'm taking the derivative of w with respect to t, and don't forget that this little guy up there is our dependent variable, and this is our independent variable. So I need to figure out, can I pull out all the t's and all the w's and together? I'm going to use properties of logs to take this and bring that down in front. So now I'm going to have 2t squared times the natural log of w plus 8t squared. Next, I'm going to factor out a t squared from both terms, and I get dw dt is equal to 2t squared. I can actually pull out a 2 from the 2 and the 8. I might as well do that now. And what I'm left with is natural log of w plus 4. So we see that this guy here is a function of t, which is going to be my g of t, and this little guy is a function of w. So this is separable. So now that we can identify separable equations, here's how you solve it. Now, here's the overall idea before I get into anything. The overall idea is if it's separable, then all you really have to do is just move all the x's to one side and then all the y's to the other side, including the dy over dx. So in other words, if you start with dy over dx is equal to g of x times p of y, you can simply multiply both sides by d of x divided by p sub y, and you get all the y's on the left-hand side and all the x's on the right-hand side. Now you want to be careful. You want to make sure that you don't have any d of a variable in the denominator. It has to be by its lonesome on the same line. And for simplicity, I just called h of y 1 over p of y. And that's just to make the notation nicer. But in reality, once you've separated it at this step, you just integrate both sides. Now, once you integrate both sides, the antiderivative of lowercase h is capital H, and the lowercase g of x is just capital G of x, and you want to make sure that you put your constant on one side. Now really, let me just mention what's happening here at this step, just to make sure we're clear. This is going to be h of y plus a constant, and this right-hand side is going to be g of x plus another constant. The constants are different. But what I can do is I can bring the constant over to the right-hand side, and so now what I'll have is h of y is equal to g of x plus c, where that c is really just going to be c sub 2 minus c sub 1. Now, at this stage in the game, you don't have to be too careful with the constant, because after you integrate, you're going to add in a constant. But for most of these differential equations, you have to be super careful where you place that constant. So you might want to start thinking about that now. Now this next example, I want to solve dy over dx is equal to e to the 2x plus y, with the initial condition y of 0 is equal to 0. So now I'm going to write dy over dx is equal to e to the 2x plus y. And using the properties of exponential functions, I can simply write that as e to the 2x times e to the y. And you'll notice now I have two separate functions, and that is in fact separable. So this is now my function g of x, and this is now my function p of y. So it is in fact separable. Now, my next goal is to bring all the y's to the left-hand side and all the x's to the right-hand side. So I'm going to write e to the negative y over dy is equal to e to the 2x dx. Now I'm just going to integrate both sides. If I integrate both sides, I get e to the negative y dy is equal to the integral of e to the 2x dx. And on the left-hand side, I'm going to get negative e to the negative y. And again, the way I like to think about these is I know that e to the negative y, the antiderivative is going to be something of the form e to the negative y. But sometimes it's easier to work backwards than just using like u sub really quickly. So I know that I'm going to have e to the negative y, and if I put a minus sign here, then I know the derivative of this becomes this term there. And you should be able to quickly recognize these things instead of having to write out u substitution for every single one of these little problems. Likewise, over here on the right-hand side, I know that I'm going to get e to the 2x. But if I take the derivative of e to the 2x, I get a 2 in front. I don't want that. So I'm going to put a 1/2 out front so that now the derivative of this guy is equal to this. Again, this is a little bit faster in my head than using u substitution. But yes, u substitution does work, and if you're more familiar with that, you can use that. Now, this is a solution, but what I want to do is I want to solve for y. So I want to solve for this little term there to get an actual equation for this. So I'm going to multiply both sides through by negative, and I get e to the negative y is equal to negative 1/2 e to the 2x minus c. And then I'm going to take the natural log of both sides, and I'm going to get negative y is equal to the natural log of negative 1/2 e to the 2x minus c. Now I can't use any properties of natural logs at this point because I have that, because unfortunately what happens here is I have an addition or subtraction here, right? If it was just the natural log of e to the 2x, for example, I can use some properties, but I can't in this case. So this now turns into y is equal to negative natural log of negative 1/2 e to the 2x minus c. So this is the general solution. But I need to find c with this initial condition that's given to me. So now if I replace 0, or y with 0, negative natural log of negative 1/2 e to the 2 times 0, so I replace the x and the y with 0, minus c, then I should be able to solve for c. So this one I want to solve for c to figure out what that value is. Now, on the right-hand side, I'm getting 0 is equal to negative natural log of negative 1/2 minus c. And the negatives, I can multiply both sides by negative 1 and get 0 is equal to the natural log of negative 1/2 minus c. And then I can raise both sides to the power of e. And that's going to give me e to the 0 is equal to negative 1/2 minus c. So now I'm left with 1 is equal to negative 1/2 minus c. So if I add a half to both sides, then I'm going to have 3/2 equals negative c. And that means that c is equal to negative 3/2. And now I'm just going to put that back into the formula for when I solve for y. So I'm going to put this back inside the equation that I have here. And so my formula for this is going to be, this is my answer now. I have y is equal to negative natural log of negative 1/2 e to the 2x, and then the c is already negative, so I have minus minus, plus 3/2. And this guy here is our actual answer. And you'll see that the funny thing is that if you look at this and you squint hard enough, you'll see that the separability, separating the dy over dx and integrating, that was the easy part. The hard part really was doing just the manipulation, solving for y and then putting in x is 0 and y is 0 and solve for c. Right, that takes a lot of algebraic manipulation, and that's usually the harder parts of the problems, not really the integration. All right, so for this guy, this is separable, so we'll start with just like what we did before. That's going to be equal to 6x times y minus 1 to the 1/3. And for all separable functions, I'm going to bring the y terms to the left-hand side and all the x's to the right-hand side. So on the left-hand side, I'm going to be given y minus 1 to the negative 1/3 dy is equal to 6x dx. And now I'm going to integrate both sides. So I'm going to integrate y minus 1 to the negative 1/3 dy is equal to the integral of 6x dx. Now to integrate the left-hand side, I'm going to have y minus 1, and I'm going to add 1 to the exponent. So that's going to be 2/3. And if I put a 2/3 in front, I'm going to have the 3/2 in front. And you'll notice that the derivative of this term is equal to y minus 1 to the negative 1/3. And on the right-hand side, I'm going to simply write this as 3x squared, and I'm going to put in my constant. All right. Now, if I were to solve for y now, so I'm going to solve for y, and I'm going to bring the 3/2 to the other side. Now, some of you may say, well, can I just solve for c here? And the answer is yes. You can solve for c at any point. It doesn't quite matter. But let's go ahead and just solve for y first. If I solve for y, then I'm going to get y minus 1 to the 2/3 is equal to, and I'm going to divide everything through by 2/3. Or actually, sorry, multiply everything through by 2/3, or divide by 3/2, and I'm going to get 2x squared plus 2/3 of this constant. Now, this here, I can just rename that and call that, I'm going to call that C1, just to make my life a little bit easier. So I have y minus 1 to the 2/3 is equal to 2x squared plus C1. And now I'm going to take both sides and cube it, and then take the square root. So now I'm going to have y minus 1 is equal to the 2x squared plus C1 cubed, and then I'm going to take the square root of both sides, and lastly I'm going to add 1. So I have y is equal to the square root of 2x squared plus C1. Oops, I went a little too far there. And add 1 on the outside of that. Now I know that if I put 1 in there, if I make my substitution, so now I'm going to substitute x is equal to 1 and y is equal to 1 from the initial condition that I have up here, and solve for c. Alright, so now I'm going to get 1 is equal to the square root of 2 plus c plus 1. Then I get 0 is equal to the square root of 2 plus c. I square both sides, and then I just get 0 is equal to 2 plus c. So that means that c is just equal to, or sorry, c sub 1, I should say, to be consistent with my notation. C sub 1 should really be equal to negative 2. Now, that means that our solution is going to be y of x is equal to the square root of 2x squared minus 2 plus 1. So that's our solution. Now here's something else that we should note. But wait. We can also see that the constant solution, y of x is equal to 1, also works. You'll notice that if y of 1 is constant, then that means the derivative is equal to 0. So then dy over dx, which is 6x times y minus 1 to the 1/3. If I were to put in the constant here, you would get 0 on the right-hand side, and the derivative of a constant is also 0. So another solution is y of x is equal to 1, the constant. So we actually have two solutions. And don't forget, this also satisfies the initial value conditions, right? We also have note that y sub 1 is equal to 1. Now you may ask, what in the world gives? We have two solutions to an ODE. And how did I come up with this one with a constant? That seems like I just pulled it out of the air. Well, eventually we're going to talk about existence and uniqueness of a solution set, which we've already mentioned a little bit before when we talked about ODEs and some of their properties. But the idea is that this actually has another solution. And we get that because if you look at this step, we divide it by y minus 1. And anytime you divide by a variable, you're going to lose an answer, right, sometimes. And so that's kind of how I knew in the back of my head that I could potentially be losing an answer. But if you were to just work the problem blindly, you would think that there's only one solution for this, and that's what we got here, when in reality there's another one. So in the future, when we start talking about testing existence and uniqueness, this is the example where it's very important to do so. So let's try this guy out. This is another separable difference equation, and we just want to solve this for general C's. So here we're going to have dy over dx is equal to x minus 5 over y squared. And note, I can write this as 1 over y squared times x minus 5. So it is in fact separable. And just like all separable difference equations, the goal is I'm going to put all the y's on the left-hand side and all the x's on the right-hand side, and then just integrate. So on the right-hand side, I'm going to have y squared dy is equal to x minus 5 dx. Now I'm going to integrate both sides. Y squared dy is equal to the integral of x minus 5 dx. Now when you integrate both sides, you're going to have 1/3 y cubed is equal to 1/2 x squared minus 5x plus c. And again, just like before, I want to solve for y if possible. Sometimes it's not possible to solve for y because you get some crazy functions, and that's okay. That's called an implicit solution. So when you solve for y, that's what we call an explicit solution. If you can't solve for y, that's an implicit solution. So if I solve for y, the first thing I'm going to do is multiply everything through by 3. So I have y cubed is equal to 3/2 x squared minus 15x plus 3 constant. And I'm going to rename this and just to a new constant, c1. Now to solve for y, I'm going to write this as y is equal to the cube root of 3/2 x squared minus 15x plus c1. Now, you'll notice that a couple of things about this problem. You can combine constants, right? If you multiply by a constant, that's just a new constant. If you subtract a constant, that's just another constant, right? If you subtract a number from a constant, that's just another constant. So when you write all this out, you'll typically just write the last term as c. And what a lot of differential equations professors do, and this kind of confused me when I was a student, was they would just write 3c as just another constant c. They just wrote c's for everything. And I was always very confused. But really what they're doing is they're just saying, okay, this is a constant, let's just call it a new constant, and so now we have this as our final answer. And when you type this in on the computer, you can just use c for the constant. So you can just use, just use c for the answer when you type that in or you put it down. All right. Now I just thought of another example as I was doing this. So let me write this out here. If I have dy over dx and I have that's equal to 1 minus y squared. Again, that's an autonomous differential equation. And that is separable. And it is separable. So let's figure out how to solve an autonomous differential equation that is separable. Just like before, I'm going to put all the y's on the left-hand side and all the x's on the right-hand side. So I have, on the left-hand side, I'm going to have 1 over 1 minus y squared dy is equal to just dx, right? And sometimes some students like to put in a little placeholder here to remind them it's just 1 dx. Now I want to integrate both sides with respect, or just integrate both sides. If I integrate the left-hand side, I have 1 minus y squared dy is equal to the integral of dx. Now, here's what you should do. You should recall from Calc 2. Recall, and again, this is from calculus. It might have been a while since some of you have had calculus, so it's good to kind of review these things. What I want to do is I'm going to write this as 1 over 1 minus y squared, and I'm going to factor the denominator. And I'm going to write that as 1 over, and again the bottom is just the difference of two squares. So that's 1 minus y times 1 plus y. Now in calculus 2, you learned that you had what's called partial fraction decomposition. So I'm going to write this as 1 minus y, and I'm going to put a placeholder in the top. I'll just call that a, plus, and in the bottom I'm going to have 1 plus y, and in the numerator I'm going to have b. The question is, what is a and what is b? Well, there's something called, and you can look this up if you don't remember this, but there's something called the Heaviside cover-up method for solving these things super fast. And here's how this works. It's going to be kind of hard to do since I can't quite cover things with what I have. Alright, so let's see how the Heaviside cover-up method actually works, just really quickly. The first thing is, I'm going to make a little box here so I can cover stuff up. The way it works is, if I want to solve for A, so if I want to solve for A, I look at the denominator. When is the denominator equal to 0? The denominator is equal to 0 when y is equal to 1. And then I can just literally cover up the 1 minus y, because that's the one I have over here. And if I put 1 inside what's left after I cover it up, I get 1 divided by 1 plus 1, which is a half. So let me move this guy out of the way and put in the a is equal to 1/2. And again, this is just a quick shortcut. Some of you may not have seen this before, but again, it's just how to do it very quickly in your head. Now for the b part, the denominator is going to be 1 plus y. So that's what I cover up, the 1 plus y. And in the denominator is equal to 0 at y is equal to -1. So the part that I cover up, I put in -1, and I get 1 divided by 1 minus -1. So that's going to turn into also 1/2. And that's pretty much how the Heaviside cover-up method works. And again, most students don't even have to write any of this out. They can just see it very quickly. 1 over 1 minus y squared is equal to 1/2 1 minus y plus 1/2 over 1 plus y. So now I'm going to substitute this back into the integral. And so now I have the integral of 1/2 divided by 1 minus y plus 1/2 divided by 1 plus y dy is equal to, now the right hand side is really easy. I can just simply write that as x plus a constant. Now on the left hand side, what I'm going to have is, I can factor out a 1/2 from both of these terms and just integrate. I'm going to have -1/2 times the natural log of the absolute value of 1 minus y plus 1/2 times the natural log of 1 plus y is equal to x plus a constant. Now, I'm also going to multiply everything through by a negative so I can solve for y. And I'll multiply everything through by 2. That'll make things actually a lot easier. So if I multiply everything through by -2, I have the natural log of 1 minus y minus the natural log of 1 plus y is equal to -2x, and now I'm going to have minus 2c1, and I'm just going to call this whole term here the negative. I'm just going to call that c2, just to make my life a little bit easier. And on the left hand side, I'm going to combine the natural logs. So now I have the natural log of the absolute value of 1 minus y divided by 1 plus y is equal to -2x plus some constant number. Alright, so now I'm going to raise both sides to the power of e. And so now I'm going to raise both sides to the power of e, and I get the absolute value of 1 minus y divided by 1 plus y is equal to, now let's see, I'm going to get e to the -2x plus c2. But if you stare at this long enough, and using properties of exponents, you see this is just going to be e to the negative 2x times e to the c2. Now I should also note that if I were to get rid of the absolute values, that would just be 1 minus y divided by 1 plus y is equal to plus or minus e to the c2 times e to the negative 2x. And this in front is just a constant. So let me just call this c. Remember, e to a number is a number. And the plus or minus corresponds to the values of what was happening on the inside of the absolute values. So it's either going to be positive or it's going to be negative. And again, a positive or a negative number is just still a number. All right, so now I'm going to have 1 minus y divided by 1 plus y is equal to ce to the negative 2x. And now remember the goal. I mean, don't get lost in all the algebra. The goal is to solve for y. I think usually the algebra is the hardest part. So what I'm going to do is just multiply everything through by 1 plus y. And I'm going to get 1 plus y times ce to the negative 2x. And then I'm going to distribute that to each term. So I have ce to the negative 2x, plus y ce to the negative 2x. Now we have this equation, and this is the left-hand side, and this is the right-hand side. Now to solve for y, I'm going to put all the y's on the left, and then everything else that's not a y on the right. All right, so if I put all the y's on the left, then let's see. I'm going to have negative y minus y times c times e to the negative 2x, and then everything that's not a y I'm bringing to the right-hand side. So that's going to be this 1 I'm bringing to the left, and I have this ce to the 2x, negative 2x, on the right-hand side left over. So that's just going to be equal to negative 1 plus ce to the negative 2x. And I'm going to factor out a y and then divide. So if I factor out a y on the left-hand side, I'm going to have y negative 1 minus ce to the negative 2x is equal to negative 1 plus ce to the negative 2x. And my final answer for all this, after all the smoke clears, after all this is said and done, I probably could clean this up a little bit, but I'm running out of room, is just going to be y is equal to negative 1 plus ce to the negative 2x divided by negative 1 minus ce to the negative 2x. And that is my final answer. And just like I said before, the hardest thing about this whole process really wasn't if you go back and look at it, it's just separating the variables. That was done in 3 steps. The hard part was remembering how do you integrate this. You had to recall from calculus the partial fraction decomposition or the Heaviside cover-up method. However you remember this, you had to remember how do you integrate this particular piece, and then you had to remember what sort of crazy algebraic manipulations and combining constants to solve for y at the very, very end. That's actually going to be the most challenging parts to difference equations. So now, here's a reminder, and this is very important. And I want to add to this list. You want to know how to do U sub, and just like I was doing before, you want to do them very quickly. Sometimes you can do them in your head. Sometimes it's more complicated, and you actually have to write out, let U be, and then make that substitution. You want to recall integration by parts, and you also want to recall trigonometric substitutions. And also, don't forget, also remember how to do the partial fractions. Like the last example I did. And so this class isn't really going to review a lot of the Calc 2 parts, so just make sure that you go back and you have that in your and you're very comfortable with it, because I'm just going to start using them. All right, I'll say, okay, this is integration by parts, and then this is trigonometric substitution, etc., etc. So please make sure that you remember those. So another quick example, I can just think of one off the top of my head, is if you have dy over dx is just equal to, say, 1 minus y squared, or 1 plus y squared, even easier. And I want to solve for this. I'm going to have 1 over 1 plus y squared. Dy is equal to dx. And then when you integrate both sides, you want to remember that the left-hand side is actually going to be the arctangent of y. And the right-hand side is x plus c. So your solution is going to be y is equal to the tangent of x plus that constant. So you can see that sometimes these substitutions and these tricks from Calc 2 are in fact very, very useful, and we're going to be using them quite a bit.